Hello all, hope you all are doing good. In today's class, we are going to learn one more important topic in database management system, which is validation-based protocols and multiple granularity. Let us see what is validation-based protocol. It is also known as optimistic concurrency control. So far, we have learned different concurrency control protocols. All these are used to ensure serializability among the transactions that are executing in parallel with each other. So we know that when the transactions execute in parallel to each other, there may occur different kinds of conflicts. In order to avoid conflicts or to maintain data consistently in the database, it is necessary for the transactions to execute in parallel, but by ensuring serializability. Serializability says that the transaction operations are to be made one after the other. Now here, we are known with the validation-based protocols, which has been given a name called optimistic concurrency control. It is because it ensures that the execution of the transaction will take place completely, or the operations of the transactions must be rolled back completely. And now, whenever any transaction takes place, all the transactions has to undergo these particular phases. That is read phase, validation phase, and write phase. Let us see what is the read phase. Transaction TI reads only to the temporary local variables. Read phase says that whenever transaction wants to view the data from the database, then it has to go to the read phase. It is only allowed to perform a read operation onto the data item. And next after the read phase, we have validation phase. Transaction TI performs a validation test to determine if the local variables can be written without violating serializability. As discussed before, serializability ensures the execution of the transaction takes place one after the other. So when one after the other, the operations are made, then it ensures the consistency in the database. In order to attain serializability, that is, the transactions are executed in parallel. As a result, every transaction has to undergo this particular validation test. If it is a non-serial schedule, then we should be able to provide the serializability. Only then we are able to retrieve the consistent data whenever we require. So validation phase will always check for the serializability within the non-serial schedules. Now let us see what is a write phase. If TI is validated, the updates are applied to the database. So that means write phase, the transaction will enter only after the completion of the validation phase. If at all a transaction wants to perform any updates to the database, then those updates are done to the database when it enters into this particular phase. If it is not able to make such updations onto the database, which means what? Due to some cause, if the transaction has failed or aborted, in that case, the operations made by that particular transaction will be rolled back. Now let us move on to the three phases of concurrently executing transactions. So not only the transactions undergoes the three phases which we have discussed before, that is the read phase, validation phase, and the other one is what? The write phase. Every transaction has also undergoes these three different phases. That means this validation based protocol is also going to maintain the three timestamps for any of the transaction that enters into these three particular phases. Firstly, we have start of TI, which means at what time the transaction has started its execution. That particular time is recorded by the database system. And validation of TI represents the time when TI entered into the validation phase. Transaction TI enters into the validation phase only after the completion of the read phase. So it is going to maintain the time at which the transaction has entered into the system, and then it is going to maintain the time at which it has entered into the validation phase. Once validation phase ensures the serializability of the transaction, then the transaction will move on to the write phase. Once the operations that are successfully made onto the database by a corresponding transaction, then it indicates the finish of transaction TI. So this particular validation-based protocol is also going to maintain the time at which the transaction has completed the write operations on the database. Serializability order is determined by the timestamp given at the validation time to increase the concurrency. Yes, this particular validation-based protocol will ensure serializability. Thereby, it can increase the degree of concurrency by reducing the conflicts. And then we have some other conditions that the transaction has to hold when it comes under the validation based protocol. So let us see what are those conditions. If for all Ti with Ts of Ti less than Ts of Tj, either of the following conditions hold. We know that the transactions are executing in parallel with each other. So when they execute in parallel with each other, the transaction should either hold this first condition or the second condition. So what are they? Let us see. T1 started at 9 o'clock and assume that it has completed all its operations by 9:30 before T2 transaction has started. So this particular condition is satisfied. If not that condition, we are going with the second one. That is, start of T2 is what? At 10 o'clock. Finish of T1 is at 10 o'clock. That means T1 completed all its operations by 10 o'clock. By that time, T2 started its execution, but not entered into the validation phase. So once it started its execution, assume that T2 has entered into the validation phase by 10:30. And now you can see the timings here. The first case, the timing is 9 and 10. This is satisfied. The second case is what? T2 transaction has started at 10 o'clock and meanwhile T1 transaction has not completed its operations, but sometime, let's say by the time 10 o'clock or by the time 10:05, T1 transaction completed its execution. And before T2 moves to the validation phase, as T1 completed its execution, we can say that it is valid. And then the data in the database is remain consistent, ensuring both the transactions are serializable. We have other 2 points, that is, the write of Tj do not affect the read of Ti since they occur after Ti has finished its reads. And the write of Ti do not affect reads of Tj since Tj does not read any item written by Ti. Let us understand these 2 points by taking an example. Here we have two transactions, say T25 and T26. Transaction T25 has started read operation on the particular data item, say B. After some time, T26 has performed read operation on the data item B. Here you can say that read operation on the same time or at different times made by two different transactions is not a problem at all because they are not trying to modify the data. They are only doing the data. After performing read operation on B, immediately T26 started performing updates on B, but it is not reflected. When it is going to reflect into the database, only once the validation phase the T26 has entered. After the validation test it is successful, then it is allowed to perform the write on the database, write onto the particular data item, which means the updates which this particular transaction wants to make on the data item B will be made only after validation is being done. Now you can observe the timings. Here, validation of T26 is made before the completion of this T25 transaction. And hence you can say that this is ensuring the serializability. Now let us move on to the other concept, which is multiple granularity. Now, what is multiple granularity? Granularity is nothing but it is the size of data item allowed to lock. Now, multiple granularity means hierarchically breaking up the database into blocks, which can be locked and can be tracked, what need to lock and in what fashion you have to lock. Such a hierarchy can be represented graphically as a tree. Now, we have an example. Let us take this example. Here we have a database, which in turn contains several areas. Every of the area is again having child nodes, say files. FA and FB denotes files of that particular areas. And every of the file in turn contains several records. So that is what is depicted in this tree like a structure. Like the first level we have is a database, and next it is having children's, and those children's are represented by A1 and A2. Those are nothing but the areas of the database, and those area in turn contains childs like files FA, FB, and then in turn files contain several records. So it is a tree-like structure. Now I'm going to take an example. As we have worked with multiple tables that we have created in the databases, assume that we have a database. Okay, in the database we have several tables that the user has been created. Let us say the tables like T1 table and T2 table. These two tables are present in the same database. Tables in turn contains what? They contain records. So let us say R1 and R2. And this contains some R3. This records in turn contains what? Every day of the record in turn contains multiple columns. Column values they contain. So let it be data 1, data 2, and data 3. Clear? So this is one level. This is level 0, which is a root directory. This in turn contains children's like tables. This table in turn contains what? Records. This records in turn contains what? Several column values or the data. So what is multiple granularity here is whenever we wanted to access the data, any transaction, if it would like to access the data, there is a possibility of locking at any particular node. Like if your transaction tries to lock this particular database, in that case, any of the transaction which wants to try to access the lower level nodes, it is restricted in doing so because there is some other transaction that is TI, let's say, it has already locked the database. So when the database is locked internally, which all tables or the records that are present inside the database will automatically get locked. So thereby the other transactions which wants to access or perform any operations cannot be done. Now, suppose that if a transaction wants to perform some operations at the lower level of the database. Let's say T1 transaction wants to lock this particular data. Locking of the data can be done in different cases. Let us discuss case 1. In case 1, if there exists a transaction which would like to lock this particular data, then in that case, it has to check starting from the database. It has to traverse till this particular level is reached. It is going to check whether this database is locked by some other transaction or not. If it is not locked, then it has to traverse this entire path and check at every level whether every node related to this particular element has been locked by the other transaction or not. If all the nodes are unlocked, then there is a possibility of the transaction to make a lock on this particular data item and then allow other transactions in restricting access to this particular data item. Now let us discuss the second case. What is the second case is if there exists a transaction which would like to lock the database itself or it would like to lock the parent node. In that case, the transaction has to check for the lower level elements, whether they are locked by any other transactions or not. If they are locked by any other transactions, it has to wait until they release the locks. Then only the transaction can perform a lock on the main root node or it can lock the parent node. So this is the second case. Now let us see intention lock mode. What is this intention lock mode? In lock-based protocols, we have learned two different locks, namely shared lock and the other one is exclusive lock. What is shared lock? If a transaction obtains a shared lock, then it is allowed to perform only the read operation on the data item. Whereas if the transaction acquires the exclusive lock, then it is allowed to perform both read and write operation on the particular data item. So if any of these locks are acquired, then the other transaction which wants to perform any of the operation at the same time, it has to wait until the transaction which acquired the locks are released. In addition to the S and X lock modes, that is shared and exclusive lock modes, there are three additional lock modes with the multiple granularity. Intention shared, that is represented by IS, indicates explicit locking at the lower level of the tree, but only with the shared locks. Let me draw a diagram. As we are discussing about the multiple granularity, locks can be made at different levels. When I say that the parent node, that is A, is intention shared lock mode, if it is in intention shared lock mode, which means the child nodes or the lower level nodes of this particular A. Here, let's say the lower level nodes are Q and Yes. Okay, these two nodes are what? They are shared lock modes. Next, let us see intention exclusive. It indicates explicit locking at the lower level with the exclusive or the shared locks. Here, if I say that the parent node, let the parent node be represented by A and it contains child nodes. Let the child nodes be denoted by Q and R. Whenever a transaction wants to perform a write operation onto this particular node or the data item, then the parent node must be in which mode? It must be in an intention exclusive mode. First, it has to be in an intention exclusive mode. Then only the transaction can obtain the exclusive lock on this particular data item R to perform any sort of changes to this item. Now let us see what is the shared and intention exclusive lock. The subtree rooted by that node is locked explicitly in shared mode and explicit locking is being done at the lower level with the exclusive mode locks. Here there is a tree. This is a tree. Assume that the transaction has obtained a shared intention exclusive lock mode for this particular root node. So this is my SIX, which is shared and intention exclusive lock. Then the subtree rooted by that node, we are talking about this part now, this particular part. Okay, this particular node is locked with the shared lock. In shared mode, this particular node is locked and explicit locking is being made at the lower level with the exclusive mode locks. That means the children of this particular node, these two are locked with exclusive locks. This is known as shared and intention exclusive lock modes. Now let us see what is the compatibility matrix with the intention lock modes. While discussing about the compatibility matrix, intention shared lock is compatible with all these locks except the exclusive lock. And so it is given with a cross mark over here. Similarly, here you can find intention shared lock. This is compatible with all the locks except this exclusive lock. So here you can find a cross mark. And coming to this shared lock is compatible with the shared lock. So therefore, it is given a right mark over here. And coming to intention exclusive, this is only compatible with the intention exclusive. So thereby it is given again a right mark. Except these, in the remaining cases, all the locks are incompatible with the other locks. And therefore it is marked with a cross symbol. This you have to remember. Next, let us see. The transaction TI can lock a node Q using the following rules. Whenever a transaction wants to obtain lock on different levels, starting from the root node, and then we have parent node, and from parent we have several child, and their child have their own childs. So at any of the level, the transaction can make a lock. So before it makes a lock, it has to understand all these particular rules that are listed over here. By following these rules, the transaction can acquire lock on that particular node, thereby restricting the other transaction in accessing the data. Hope you have understood today's lecture. Thank you.